for this problem, we're supposed to find a point or points on z equals 3x squared minus 4y squared, at which the n arrow is equal to 3, 2, 2 is normal to the tangent plane. So we kind of have two different things going on here, but we have to reconcile them. So we have this graph, this surface, this f of xy, right, given by that equation. So that's some surface. And then we have separately this vector here, which we want to be normal to the tangent plane of this surface. So that's how they come together. So first of all, what I want to do is work with this normal vector here and kind of apply it to what we know about planes in general. So what we can do is take each of these components, so the x, y, and z components, and stick them on to be coefficients for each of those respective variables. And then we'll set it equal to some constant d, right? So this thing that I just wrote here, what I just created, is an equation of a plane, right? Of a plane. And more particularly, more importantly, we have, this is an equation of a plane with normal vector of 3, 2, 2, right? Because that's what our coefficients for x, y, and z are respectively. Okay? So we're just going to keep this in mind. So kind of just follow us around through the problem, okay? And it'll come back in the end. So anyway, so now let's approach it from the other point of view. So we'll work with what we're given, our z, which is equal to a function of x and y, right? So that was given by 3x squared minus 4y squared. And now what I want to do is kind of work more toward the equation of the tangent plane in particular, okay? So in order to work toward that, we do have to find our partial of f with respect to x. So that's going to be equal to the partial with respect to x of 3x squared minus 4y squared. So if we do that, we're just going to get a 6x. Okay, and then let's do the same thing for y. So we're going to find the partial with respect to y. So 3x squared minus 4y squared. So that'll just come out as being a negative 8y. Okay? So more importantly, when we do plug these into the equation of the tangent plane, remember we have to plug it into a certain point. So into a certain point AB, and then that f of AB, right? So when we do that, we need f sub x of AB, of some point AB. And that's our goal for this problem, is to find that, what is that AB, and then f of AB, right? We want that point here. What is this? So anyways, if we plug that in, and AB into there, what we get is a 6 times a, which is just a 6a, right? If we plug in that a for x. And then we have f sub y. If we're evaluating at some point AB, that would just be a negative 8b, okay? So, and I don't need the equal sign there, but we're just going to keep these things that I just found. We're going to keep these in mind. We'll kind of like put them away for storage until the end, where they'll come into play, all right? Okay, so now what we're going to do is actually just construct the linear approximation for our tangent plane. Okay, so z is equal to f of AB, and then plus f sub x evaluated at AB. So see here, that's one of the things that we'll need later on. And then times x minus a plus f sub y evaluated at AB. Again, that's something else we found on the last slide. And then times that y minus b. So how are we, this is the equation for the tangent plane. This is our linear approximation. And then I'm going to recall this formula, or this equation that we constructed, right? So how are we going to make this top thing, the thing in the box, the equation of the tangent plane, resemble something like down here? Well, we can start by observing that in the equation that we want to get it into the form of, all of our variables, our x, y, and z, are all on the left side, right? So these are the variables, and on the right side we just have some constant. So let's try to rearrange our top formula to look something like that. So the first thing I'm going to do is say z is equal to f of AB, and then what I'm going to do is actually distribute this f sub x term, okay? So if I distribute that, I get f sub x evaluated at AB times x minus f sub x evaluated at AB times an a. And then I'm going to do the same exact thing with this f sub y. I'm going to distribute that to both of those inside terms. So f sub y evaluated at AB times y minus f sub y, again at AB, times a b. I'll just write a b there. Okay, so see here how we have a separate z term a separate x term and a separate y term. So what I'm going to do is move these guys over to the left side, the x and the y term, so we can get all the variables on the left, and then we will just leave the constants on the right side. So what we'll get is a negative f sub x evaluated at ab times an x minus f sub y evaluated at ab times a y plus z is equal to f of ab minus f sub x evaluated at ab times an a minus f sub y evaluated at ab times b. Okay, so see here how we got all the variables on the left side and all of the constants on the right. Okay, so now it's basically in this form that we want here on this line, except for we do see that there's a difference, well, other than there being a whole bunch more variables on the bottom, right? But anyways, so what we do see, how can we make these even more similar, is what's catching my eye is this z term here, right? Because you can't really change anything on this bottom equation with regards to the z, except for the coefficient, right? Because there's no like f term, or like we don't have to use the function in any way when dealing directly with the coefficient of the z. So that means that in order for these equations to become exactly equal, we have to get a 2 in front here. And the only way to get a 2 in front of the z is to multiply the entire equation, both sides, by a 2. Okay? That would be the only way to get a 2 in front of the z. So let's do so, and we get a negative 2 f sub x times ab times an x minus 2 f sub y of ab times y plus 2z. So we get that 2 there, so that's good. And then we get equals 2 times all of this stuff on the right side, minus f sub x at ab times a minus f sub y at ab times b. Okay, so now what we see, again, I'll rewrite this equation down here on the bottom. So we have a 3x plus 2y plus 2z is equal to some constant d. So we see that these two z's now match up, so that's good. And now we need to actually just compare I'll start with the left side, because this right side, that would be super messy, I think, because we don't even know what d is, right? So we're not going to deal with the right side at all. All we'll need is the left side here. So what we're going to do is compare the coefficients of the x and the coefficients of the y terms, okay? And we'll do that on the next slide. Okay, so I'll just rewrite what we had on the previous slide here. So we just had a negative 2 times f sub x of ab times x, and then a negative 2, or a minus 2, f sub y at ab times a y, plus our 2z is equal to 2 times a bunch of other stuff. I'll just rewrite that real quick. We won't need it. I'll tell you right now, we do not need this right side to figure out the rest of the problem. But I'll just write it for our reference. Okay, AB, there we go. Okay, so we have that, and then we had 3x plus 2y plus 2z is equal to some d. So we're not going to pay attention to the right side at all. We won't need that. The two z's match up, that's good. And now we need these ones to match up as well. So the coefficients of the x need to match up, and as do the coefficients of the y. So we'll start with the x. So we get negative 2 f sub x at ab must equal a 3. Okay? And now something important to note is that, remember those f sub x at ab? We figured that out to be a 6a. Okay, remember that from a little while ago when we differentiated with respect to x and then differentiated with respect to y. We took the partial derivatives, and then we kind of plugged in that a and b. So we got 6a for the f sub x one equals 3. So now what we can do is basically just solve for a. So if we do a, that's going to be equal to 3 over negative 12. So that would be a negative 1 over 4. Okay, so we found our a. That's good. One part down. And now let's compare the coefficients of the y. So now we have negative 2 f sub y at ab, and that's going to be equal to a 2. And remember, we found that this f sub y was equal to negative 8b. Okay, so then we have a negative 2 over here. All right, so that's going to be a 2 there. This, on the left side, we're going to have b is equal to 2 divided by 16, a positive 16. So that'll be a positive 1 over 8. So that would be our b. And now we are almost done, but our point, the answer is not just negative 1 1 over 8, or sorry, negative 1 over 4, 1 over 8, but we have to have that last term, which is equal to f of ab. Okay, so the way to get this is we're going to basically just plug in our negative 1 over 4 and 1 over 8 into our original function, which was z, which is equal to f of xy, is equal to 3x squared minus 4y squared. Okay, so we'll do that on the next slide. We're just going to plug in this negative 1 over 4 and 1 over 8 into this equation there. Okay, so if we do so, then we're going to get that z, also known as f of negative 1 over 4, 1 over 8, is going to equal 3 times a negative 1 over 4 for x squared minus a 4 times 1 over 8 squared, okay? And that's positive 1 over 8. All right, so if we continue solving, we're going to get that z, our z coordinate, is going to be equal to 3 times 1 over 16, and then minus 4 times 1 over 64. All right, so this is going to be 3 over 16 minus, and this will be a 1 over 16, which is equal to 2 over 16, which is then equal to a 1 over 8, a positive 1 over 8. All right, so we have that a is equal to negative 1 over 4, b is equal to 1 over 8, and c, or our z coordinate, also known as f of ab, is equal to also a positive 1 over 8. So that will be the final answer. This is our point, negative 1 over 4, positive 1 over 8, and positive 1 over 8.